two different rubidium, strontium, neodymium, samarium. Because this is incompatible element enriched, it's enriched in the parent here and the daughter here. And so this will end up with preferentially high strontium isotopic compositions, 87, 86, and low neodymium, 143, 144. The inverse is true for the mantle. It has low strontium 87, 86. 87 is the radiogenic daughter to rubidium 87, and it'll have high neodymium. And so these are complementary. So if there was a fractionation, formed different reservoirs, isolated over long periods of time, you should see an inverse correlation between those two isotopes in the rocks. And this is the characteristic mantle array. And so in this quadrant, you're looking at things that would be generated from a source region that had long-term depletions in incompatible elements. In this quadrant, you're looking at rocks that were derived by melting of reservoirs who had suffered a long-term enrichment in incompatible elements. And in fact, you do get a nice negative correlation, and this is called the mantle array. There's a point in the middle there that's bulk silicate earth. How do we know what the starting point was? What's our reference?
Chondrites?
Excellent. Not the moon, because the moon formed after. I know. Well, you sort of. You did. You did.
I was going to
Okay. But we look to meteorites. Okay, and meteorites give us the best clue as to what those primordial starting compositions were. Not perfect, but a better clue. Okay. So this is all fractionations caused by long-term evolution of the mantle by mantle melting. All right. So that's the flux out part of the reservoir. Now, what about the flux in? And we do that by the garbage disposal of the earth, which is subduction zones. The partitioning or the fractionations here are between a fluid and a rock. And so elements that like to be in fluids are ones that have, they are bigger and so ionic. So it's the charge divided by the radius. So if it has a low charge and a big radius, it has a high ionic potential, and polar water molecules like those and will tend to hold on to them. And so we have a completely different group of elements that then track this dehydration process. In particular, potassium, rubidium, barium, strontium, and lead are elements that get partitioned into a fluid during dehydration. So we have fingerprints that we can track how does the composition of different reservoirs change as a result of a process, and we can tell the difference between processes going on during subduction and processes caused by melting, flux out and flux in. Yeah. Okay. And so we can look at magmas derived from different parts of the mantle, and we can try to say something about what are the processes that have affected that. And you can look lead enrichment in the continental crust, neodymium depletion in the continental crust, whereas neodymium is enriched in these enriched things that come from oceanic islands, and lead is depleted. So we can see complementary sorts of relationships in the trace element geochemistry. And so in summary, mid-ocean ridge basalts are derived from depleted mantle that has suffered depletion of incompatible elements, and it's been sitting down there long enough that it has a depleted radiogenic isotopic composition. Oceanic islands have variably enriched trace element compositions and indicated that they have gained flux in through the process of subduction. And continental crust is, long-term enrichment in these incompatible elements and enrichment in fluids. All right. This is a diagram that, again, this is, when I give a talk, this is just, everyone just knows exactly what it is. And it's just a mess for you guys. But I'm just going to use two. This is going to be my indicator diagram for initial composition. This is lead 206, 204. And so the ingrowth from decay of uranium, strontium 87, 86. Strontium 87 is from the ingrowth as a result of decay of rubidium 87. And we have arrays in this direction, and then we have arrays in this direction. And people have agreed pretty much that in this direction we're looking at contributions from continental crust. Okay, so this is garbage in from subduction. This is garbage in from subduction, but it's dehydrated oceanic crust. And then this is 30 years of debate. Is it primitive mantle? Is it less depleted mantle? What the hell is it? And so, the data to generate this diagram has taken about 40 years, and people still can't figure out exactly what's going on.
What is the margin of errors? Because
Oh no, it's smaller than the size of symbols. Okay, so a lot of it has to do with each technique. So whether we're looking at trace elements, or whether we're looking at radiogenic elements, or whether we're looking at volatile concentrations, or whether we're looking at stable isotopes, or whether we're looking at major element compositions, everybody sees a different piece of the elephant. Okay? If you remember one thing, you can remember this diagram. Everybody sees a different piece of the elephant. What I have done, and you might not believe me by the end because it gets complicated, but really I've come up for a model for the whole elephant. And I'm really excited about it. And it's through the use of volatiles, and it's the volatiles that not only allow us to trace the process, but they control the process. Okay. We won't go into that. Part of the problem is, one of the dilemmas is that the mechanism that I've come up with requires melting below the depth of arc melting, and you really shouldn't be able to melt there. But when you add the volatiles in, I will show that you can. Don't worry about that. All right, so why are volatiles so hard? You're on. Open it. Since I'm the dean, I'm going to go long. Okay, so why have I spent my life on two compounds, water and CO2? When things started, they were looking at major elements, and then the analytical techniques developed that they could start to measure these trace element concentrations, and then they developed the techniques to measure isotopes, and at first they could only measure argon, potassium argon, and then got rubidium strand. So the isotopes came online as the techniques developed. Do it.
Sure.
Yep, do it. Pop it. All right. And then, so we started the trace elements, and then we get the isotopes, and volatiles are hard. Pour me a glass. And then
just water and carbon in there.
Okay. Then serve it up, and the front row gets dibs. All right, so that's me, by the way. Kilauea in 1983, when I was young and a little bit foolish. All right, so what's going on in this glass?
Tiny bubbles.
Tiny bubbles. Okay, so the champagne was under pressure in the bottle, and that's what the cork was for. You suddenly uncork the bottle, and the pressure changes. And so those elements that are dissolved in the liquid under high pressure, suddenly at low pressure, they don't want to be dissolved anymore. They want to be a gas. They are atmophile, not magmophile or lithophile or chalcophile or any of those lovely words. They want to be a gas. The same is true of magmas. When we generate them in the mantle, very high pressures, concentrations of carbon dioxide and water dissolve into that magma. As that magma ascends and depressurizes, it sits in the crust for a while, it loses some gas there, and then during eruption, it loses the rest of its gas. What is driving that lovely fountain of magma is the exsolution, volume expansion of gas that at high pressures is dissolved in the magma. At low pressures, it becomes a gas and it expands. The volume expansion of gases is much greater than the volume expansion of magmas or solid rock. And so that's what drives our eruptions. The reason why arc volcanoes explode and mid-ocean ridge volcanoes don't explode is twofold. One is the initial concentration of water and CO2. Arc volcanoes sit about 100 kilometers above the subduction zone, and all this water has been added, which has led to the melting, which leads to our arc volcanoes. So they have high initial concentrations of water and carbon dioxide, and so when that pressure gets released, they have more volatiles, just like the champagne. If we uncorked wine, it didn't have a high concentration of initial volatiles, it wouldn't pop, but champagne has a higher concentration of initial volatiles, so it pops. All right, so one problem is differences in the initial volatile concentration. The other is pressure of eruption. And so at mid-ocean ridges, we're talking about pressures of sort of 300, 400 atmospheres. And so at a mid-ocean ridge, you're able to have a higher confining pressure, and so much or most of the gas will stay dissolved in the magma as it is quenched to glass at a mid-ocean ridge. So if we uncorked that bottle, poured it in the glass, and put it into liquid nitrogen, and generated a champagne ice, and then we were able to somehow analyze that champagne ice, we would have some bubbles in there, we'd have higher concentrations dissolved in the liquid that hadn't exsolved out yet, and we'd get a pretty good idea of what the initial volatile concentrations are. That's what I do. I look at mid-ocean ridges and oceanic islands, in particular the submarine erupted magmas, like around the margins of Hawaii, you know, the Galapagos, and I look at where hotspots or plumes contribute magma or mantle, a geochemical signature, to mid-ocean ridges, so that I can get these things that have been rapidly frozen in the glass that quenches on the outside of basaltic pillows. Everybody seen a basaltic pillow? Geological Oceanography, you've seen it?
Yes,
You borrowed mine?
just yesterday.
Okay. Little black rind on it. That's what I study. All right. Okay, there we go. Why are volatiles so hard? Why were they the last thing to get added? Because it's hard. So I go out on ships. This is the Western Flyer from Mbari. This was the ROV Tiburon. And these were some seafloor pillow basalts. And if they're erupted at a higher magmatic flux rate, you get more sheet flows and more pavement of basalt. Collect glass from those puppies. Saw them up. You get little things like this, little chips of glass. Doubly polish them to a thickness of roughly 200 microns, measuring them with a digital micrometer. Analyze them on a Fourier transform infrared spectrometer. So, and this infrared spectrometer moved with me from Miami, and it's in the geology department. And so we, as a college, have access to an infrared spectrometer, if anyone, and I have a microscope. And so I do transmission, spectroscopy, in an infrared microscope to get a spectrum. And then part of my PhD thesis was doing all the calibrations, so I can measure a peak height, boop, 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 or boop, 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 and can from that get a concentration of what was in the glass and in the magma. And then once you get all those concentrations, you can start looking around the world, and you can figure out how water behaves during standard processes that impact magmas, like crystallization, a degree of partial melting. Water behaves like cerium in between lanthanum and neodymium, so it behaves like a light rare earth element. It is incompatible. There, I brought you back. Water behaves like an incompatible element. Okay. What's the standard model out there for stable isotopes? So it turns out that during dehydration, it is always true that with lithium, water, and boron, it's the heavy isotope that goes into the fluid, the lighter isotope that remains behind. So this is the state of art, most recent published paper on our predictions for what the recycled garbage, which then gets mixed up in and pops out again in oceanic islands, looks like. And so the existing state-of-the-art model is you've got altered oceanic crust. During dehydration, the mantle wedge, which melts to form arc volcanoes, is enriched in the heavier isotope. So for delta D, it would be -10 to -40 per mil. And the lighter, the residual slab that's